Hi, my name's Radio. I like hats, One Piece, and Beyblades. You can call me other things starting with R, and I'd probably still answer. I have a chemistry exam coming up on Monday, but frankly, I'm very much out of willpower to function normally. In fact, I can barely drag myself to school, yet now I have to revise for an exam. Thus, I decided to make revising for the exam a bit more enjoyable than just regurgitating the info. Instead, I've decided to murder and kill my science workbook while making it a YouTube video, while also going over the material needed for the exam. And as a bonus, I'll be doing the same to my Russian workbook. Doing so will enable me to possibly help any other poor souls who might want to learn stuff about high school chemistry. I'm also making this with the prejudice that you, of course, have relatively good prior knowledge of chemistry. I will also be making an Estonian version of this video, probably, most likely, which I will put in the description. And of course, as a disclaimer, not everything I say might be 100% correct, since this video is just me having fun revising, and I mostly had to translate the words from Estonian to English, because the vocabulary associated with chemistry is pretty rich with weird and difficult words, which aren't always the same in every language. I have also divided the video into two big parts. In the first one, I lay the foundational knowledge needed for the exam, and the second part dives more deeply into organic compound classes. But without further ado, let's chemistry, fuck it. Since the exam is mostly organic chemistry, for the first part I'll be going over the prefixes we use in chemistry, as well as any other basic things that may need to be used throughout the exam. Firstly, the prefixes. You probably already know them, but basically they are used in compound naming to indicate the number of atoms of an element present in the molecule. So for example, carbon dioxide, which shows us that there is 2 molecules of oxygen. The other prefixes are in this table, but mono is not used much, since it would have to be added basically everywhere. There are also prefixes dependent on the number of carbon atoms present in the molecule. For example, C6H14 is hexane, since there is 6 carbon atoms in the compound. The rest are given in this here table. They are used in naming basic, but also more complex compounds, which we will talk about later. Of course, you must know how to solve all sorts of chemical equations, and balance them as well. You'll also need to know how what reacting with certain compounds is called. Burning or oxidizing is reacting with oxygen, reacting with hydrogen is called hydrogenation, and reacting with water is called hydrolysis. I'd also like to point out that in organic chemistry, with a complete burning reaction, the outcome is always CO2 and H2O, except with amides and amines. You need to know how to present different compounds with different visual structures, such as the structural formula, where you show how each individual atom is connected by lines, the condensed formula, where you show the compound carbon by carbon, and what is attached to said atom bears an index showing how many of it is attached to the carbon. And finally, the line diagram, or skeletal structure. This one can be a little confusing at first, but basically every end of a line represents a carbon, unless it's attached to something else. With the skeletal structure, we don't mark any hydrogens. You have to recognize different compounds represented with each structure and be able to name them using different suffixes and prefixes according to the given compound class. You also have to know where in the said structure lies the functional group, but more on that later. You'll have to know how to make isomers. Isomers are molecules with the same molecular formulas, but different arrangement of atoms. This is quite easy, since you just have to rearrange the compound. And please don't add things to it, just rearrange them. A bit more difficult is having to find the connections between a compound structure and its characteristics. Here you will have to know how to find the melting temperature, boiling temperature, and the density, and how well something dissolves in water. Thankfully, you don't have to find any exact values. Usually these exercises are given to you in a form where you compare one compound to another. Melting temperature and boiling temperature are dependent on how long and branching a compound is. The longer it is and the less it branches out, the stronger the compound is, because a long compound means a lot of bonds between molecules, and branching compounds result in the intermolecular pulling forces to be weaker, thus giving the compound a lower boiling point and melting point. The same logic works on density as well. Since longer compounds have stronger forces tying them together, they are more compressed and dense. How well something dissolves in water depends on how similar the polarities are between the given compound and water. For example, ethane doesn't dissolve in water, since the polarity is completely different. But ethanol dissolves really well, since the hydroxide gives it a similar polarity to water. You'll have to know all sorts of things associated with polymerization. What is an addition polymer, the addition polymerization, copolymer, polycondensation, and what is a condensation polymer. You need to know how to make repeating units or monomers out of different compounds. An addition polymer is when a monomer containing a carbon-carbon double bond add to each other, creating a long chain without losing any atoms or molecules. Addition polymerization is the reaction where two monomers combine to make an additional polymer. A copolymer is a polymer that is made out of two or more different monomers. Polycondensation is a chemical process where two or more monomers react, forming a polymer while releasing small molecules like water or rarely alcohol as byproducts. A condensation polymer is a type of polymer formed through a condensation reaction, where monomers are linked together with the release of a small molecule, which is typically water. Notable condensation polyesters, I'll point out, are polyethylene. Some notable condensation polyesters, I'll point out, are polyethylene terephthalate, or PET, which is used in plastic bottles and clothing fibers, and a natural condensation polymer is cellulose, which is used as an important structural component of plants. Some notable condensation polyamides, I'd point out, are nylon, which is used as a durable synthetic fiber, and Kevlar, which is known for its use as bulletproof material and in boat or aircraft bodies. A simple thing to remember with polycondensation is that the result is always something plus water. So while writing the reaction, one of the compounds always loses a hydrogen and the other a hydroxide. I'd suggest to circle the hydroxide and the hydrogen with a pencil or something to make it a little easier for yourself. This isn't necessary, of course. Additionally, I'll have to know the effects of phenols and halogenoalkanes on the environment and humans, as well as environmental problems. Additionally, I'll have to know the effects of phenols and halogenoalkanes on the environment and humans, as well as environmental problems in Estonia. The acute toxic effects of phenols may include the death of animals, birds or fish, and death or low growth rate in plants. Longer term effects may include shortened lifespan, reproductive problems, lower fertility, and changes in appearance or behavior, both in the environment and in humans. Halogenoalkanes can cause ozone depletion and potentially contribute to global warming. To humans, it can cause liver damage, neurological disorders, and cancer. An environmental problem in Estonia is the oil shale producing high levels of phenol in the air and water, especially in eastern Estonia. With that, the foundation has been laid. I will be using the information used in the first part from here on out, so you're gonna need the information there. Anyhow, now we can go more into detail about the organic compound classes. Which leads us to the first compound class, alkanes, which always carry the suffix -ane. An alkane is an acyclic hydrocarbon, meaning it consists of hydrogen and carbon atoms arranged in a linear structure in which all the carbon-carbon bonds are single. With alkanes and the other classes as well, you're gonna have to know the more basic or used compounds from the class, what they are used for, and if they have one, an alternative name for it. These alternative names are what you call the compound in day-to-day life. For example, sodium chloride is known as edible salt. With notable alkanes, I'd go for methane and propane. Methane is a natural gas used for LPG gas, and propane is used for heating, but also as part of LPG. Naming alkanes can be a bit difficult. If it's a non-branching alkane, it's easy. You take the amount of carbons in the compound and add the appropriate prefix and class ending. So C6H14, for example, is hexane, 6 carbons, and as it's an alkane, it has the ane suffix. When naming an alkane with a branch, identify the longest continuous carbon chain, the parent chain. Determine any branches attached to it and number the chain systematically, starting from the end closest to the branch. For example, with this isomer of hexane, the formula is the same, C6H14, but it's called 2-methylpentane. The last part comes from the parent chain's carbon amount, the first part marks on which carbon the chain splits off of, and what it splits off to, in this case, methane. It can split off into something other than methane, but if it's longer than the parent chain, you'll have to take that chain as the new parent chain. Alkanes can also turn into halogenoalkanes, where a carbon has simply switched out one of its hydrogens for a halogen, often chlorine, bromine, fluorine, or iodine. Naming these is the same, except you're naming the halogen that's branching off. For example, 1-bromopropane. The second class is alkenes. They carry the suffix -ene. Alkenes aren't much different from alkanes, but what makes them recognizable is a double bond, usually between two carbons, which also gives them a higher boiling point and melting temperature. Keep in mind that when this bond is broken, the chain will become branched, for example with butene. We may list alkenes that have a double bond as unsaturated. In the polymerization process of alkenes, the double bond is broken and it becomes saturated. Polyalkenes are the usual plastics we all know and love. They have pretty complicated names, so just remember the abbreviations. I'd mention PVC, used in pipes, doors, windows and more, but also polyethylene, or PE, which has two forms. First is low-density polyethylene, LDPE, which is soft and flexible, used for bags and packaging, and high-density polyethylene, HDPE, which is stronger and more rigid, used for bottles, pipes and containers. Naming alkenes is pretty much the same, except you have to point out where the double bond is located. So for example, 2-pentene, the double bond is between the second and third carbon. With multiple bonds, you add the appropriate suffix, diene, triene, and so forth. You may also see ethene and ethylene and wonder, what the hell am I looking at? But they are the same thing. For notable alkenes, I picked ethene and propene. Ethene is often used in industrial reactions, for example polymerization, and propene is used as a starting compound to make petroleum. Third class is alkynes, suffix -ine. You'll recognize them thanks to the triple bond, which also gives them higher boiling points and a melting temperature. Naming them goes by the same rules as alkenes, except with the suffix -ine. Again, triple bond can be listed as unsaturated. In polymerization, the triple bond is broken and the compound becomes saturated, and same as with alkenes, the chain becomes branched on either end of the triple bond. Notable alkynes include ethene and propene. Ethene is used for welding, since when it reacts with oxygen it produces high temperatures, and propene is used as a rocket fuel and in synthesis of other compounds. The fourth class is alcohols. Who doesn't love alcohols? I don't. Ending with the suffix -ol or prefix hydroxy, recognizable for having OH in the compound. During polymerization, the hydroxide, the OH, loses a hydrogen and becomes oxygen with a free bond. A dialcohol, which has two hydroxides, will lose them both. You'll have to know how alcohol fermentation works on a basic level, basically glucose reacts with oxygen and it turns into ethanol and carbon dioxide. How ethanol reacts in the human organism and its physiological effect. Alcohol reacts with oxygen, producing ethanol and water. Ethanol also reacts with oxygen and turns into ethanoic acid. Ethanoic acid burns and turns into carbon dioxide and water, which is a complete burning reaction. If I ask to summarize this process, I'd write ethanol reacting with oxygen, turning into carbon dioxide and water. Of course you'll have to know how to balance these reactions as well. Knowing the effects of alcohol on the human organism is also necessary. Of course, constant consumption of alcohol leads to addiction, memory problems, liver damage, and eventual fall-off in society, as most likely an alcoholic loses their job and income and so on. I mentioned it in the beginning, but alcohols are very similar in polarity to water, so they often dissolve very well in water. For notable alcohols, I bring methanol and of course ethanol. Ethanol is used in alcoholic drinks and as disinfectant, and a lot more actually. However, methanol is a very, very toxic alcohol used as a chemical building block, fuel source or solvent. There was an incident in 2001 Estonia where someone sold methanol and it had severe health effects on those who bought it, or consumed it. Some even died. I just thought I'd point it out, since knowing it might give you some extra points. The fifth class is amines. Suffix amine or prefix amino. If you see the NH2, H2N or NH somewhere, you'll know that it's an amine. As I mentioned, when naming amines you have two options, either the suffix amine or the prefix amino. During polymerization, the nitrogen, NH2, loses one hydrogen and becomes an NH with one free bond. A diamine, an amine with two functional groups, will lose a hydrogen in both NH2s. A diamine will lose a hydrogen from both classes. Noteworthy amines actually include dopamine, which we all know plays a role in reward, motivation and pleasure feelings, and so forth, and also ethanolamine, or MEA, which is used for removing carbon dioxide and as a corrosion inhibitor, aka to slow down corrosion. Sixth class is arenes, the suffix benzene, a very freaky class. You'll recognize them instantly because of the big ass bolt present in the compound, called a benzene core or a benzene ring. It can be marked as a hexagon with a ring or a hexagon with a double bonds over every one carbon. During polymerization, the benzene core has something else attached to it, and that attached compound will lose either a hydrogen or a hydroxide. When reacting with halogens, for example with chlorine, it will replace one of the hydrogens in any of the corners of the benzene core, resulting in chlorobenzene and hydrogen chloride. Notable benzenes are benzene itself, being mainly used as an intermediate to make other chemicals, and toluene, used as a solvent for paints, adhesives and such, or as an additive for gasoline. Phenols also include a benzene ring. The seventh class is aldehydes. The suffix is al. I'll be honest, I wasn't in school when the class talked about aldehydes, so I don't understand them as well as the others. But when looking for aldehydes, you may also run into aldehydes with the suffix dehyde. However, I don't exactly know if there's a difference between the suffixes' meanings. Recognizable by the aldehyde class CHO, where the carbon is double bonded to the oxygen. During polymerization, the double bond is broken and the oxygen receives a free bond. Notable aldehydes include ethanol, commonly found in coffee, bread and ripe fruit. It contributes to hangover symptoms, since it's produced in the metabolism of alcohol. Vanillin, which is the main flavor component of vanilla beans, and is also used in perfumery. The eighth class is carboxylic acids. The suffix is ic acid, IC acid. Also quite easily recognizable because of the carboxylic acid class, COOH. Carboxylic acids form hydrogen bonds, which are the strongest molecular bonds and give these acids higher boiling and melting point temperatures. During polymerization, they lose a hydroxide from the carboxylic acid class, COOH. A dicarboxylic acid will lose two hydroxides, one from each carboxylic acid. When reacting with metals, the acid switches its hydrogen out for the reacting metal. Carboxylic acids have a lot of notable compounds. Methanoic acid, or formic acid, is found naturally in some ants and may also be used as an antibacterial agent, but also much more. Ethanoic acid, or vinegar acid, is obviously known for being in vinegar, thus the name. It gives vinegar its characteristic smell. The ninth class is esters, suffix -oate. Esters include the COO ester class and are quite often, but not always, polymers. Esters and amides are derivatives of carboxylic acids. We get esters when a carboxylic acid's hydrogen has been switched with an alkyne. This process is called esterification. I haven't seen in this reaction an alkane, I think, ever, but the naming uses the alkyne suffix, so I'm not exactly sure what this entails, but I don't think it matters much. It's in this process a carboxylic acid and an alcohol react, and to put it easily, the combined compound loses a water molecule. So take away the hydroxide from the carboxylic class's functional class and the hydrogen from the alcohol's functional class. You can have an imaginary line that separates the two connected classes. The ester you get is written down a bit differently. You take the carboxylic acid and then flip the alcohol and connect them. It sounds weird, but with pictures it's pretty easy. It should be pretty easy to understand. When naming esters, you start from the back and name them based off of the amount of carbons. Here that imaginary line comes in handy. You count the carbons on the second half and add the OH suffix, and then count the carbons on the first half and add the "-il" suffix. So for example, CH3COOCH3 would be split between the oxygens. The last half has 1 carbon and the first half 2 carbons. Hence it's named methyl ethanoate. I personally find this ester shit pretty complicated, so if my explanation is difficult to understand, Google another one. It may help clear things up. In ester polymerization is where compounds with double functional groups come more into play. In these reactions, carboxylic acids lose a hydroxide, alcohols lose a hydrogen, making the polymer itself connect what remains of the acid and the alcohol and put free bonds on both ends. Ester hydrolysis means an ester reacting with water. This means the ester becomes an alcohol and carboxylic acid again. This is quite easy. Separate the polyester and add the hydroxide and hydrogen back to their individual compounds. Some notable esters are ethyl ethanoate, a flammable liquid used as a solvent in paints and coating with a fruity sweet odor, methyl salicylate, or wintergreen oil, a colorless liquid with a fruity odor reminiscent of root beer, known for use in fragrances and also as a flavoring agent. The 10th class is amides, not to confuse with amides. The suffix is amide, and a prefix that I've rarely heard is amido, a pretty easily recognizable class. When you see CONH2, it's an amide. As mentioned before, a derivative of carboxylic acids. When we replace the hydroxide OH in the carboxylic acid group with an amino group NH2, we get an amide. So basically, we get an amide when an amine and the carboxylic acid react with each other. During polymerization, the NH2 of an amide loses a hydrogen and the acid loses its hydroxide. Notable amides include nylon, which we mentioned before, used as a durable synthetic fiber, and lidocaine, which is a light anesthetic which blocks the nerve signals ending at the skin. The 11th class is carbohydrates. The suffix is -ose. Carbohydrates have both CHO aldehyde and OH alcohol groups in the compound, but they are usually quite easy to spot since their structures are easily recognizable. A carbohydrate structure is often in a tree form, standing upright or as a hexagon with a blackened out front, making it look a little three-dimensional. Carbohydrates are divided into 3 groups, based on the number of carbons they have. The first group is monosaccharides with 5 to 6 carbons, glucose for example. The second is disaccharides. This is what we get when 2 monosaccharides combine. Sucrose, for example, our common everyday sugar, and lactose, the carbohydrate found in milk. During polymerization, 2 monosaccharides combined, one of them loses a hydroxide and the other a hydrogen. Thus, they are connected by an oxygen molecule. The outcome is a disaccharide or a polysaccharide and water. The third is polysaccharides, long chains of carbohydrate molecules composed of several smaller monosaccharides. They form out of the remains of a monosaccharide reaction. Example, when glucose reacts with water, we get C6H10O5 N times N, which is the remains. Put a lot of these together and we get a polysaccharide. The most known polysaccharides include starch, glycogen, and cellulose. Starch is an energy storage for plants, glycogen is an energy storage for animals. There's also oligosaccharides, which are made of 3 to 10 monosaccharides. More than that, and it's a polysaccharide. 12th is proteins. They aren't exactly a compound class, and they have no special suffix or nor prefix, but knowledge about proteins is needed in the exam. Proteins are polymers made out of amino acids. Proteins form peptide bonds between carbons and nitrogen. The importance of proteins stands in the structure of organisms and what covers them, like skin or hair, and their use as catalysts in chemical reactions. They also transport substance in the human body, in the organisms. Proteins are sensitive to external influences since external influences can break their bonds. Firstly, with high temperatures, for example frying eggs or giving your hair locks. or reacting with acids. And last but not least, there's fats. Again, no special suffix or prefix or class, you just need some ball knowledge on fats. We get fats when fatty acids and glycerol react. A fatty acid is a carboxylic acid with 10 or more carbons. The fats are hydrophobic. The importance of fats is, number 1, to store energy storage in the body, and 2, fat-soluble vitamins such as vitamin A, D, E, and K. You get fats from fatty meats, fish, or plant-based oils. Fats break down into glycerol and fatty acids. Fats can also react with bases, for example to make soap. When fats react with sodium hydroxide, we get glycerol and fatty acid sodium salt, which is actually soap. Fats divide into unsaturated and saturated fats. Unsaturated fats are usually liquid at room temperature, found in vegetable oils, fish and nuts, for example olive oil, salmon, sesame seeds. Saturated fats are usually solid at room temperature, found in meats and dairy products, for example butter, cheese and red meat. There we have it. I have pretty much taught you the entirety of 11th grade chemistry. Yes, not the best teaching, I'm not a damn teacher. But now you should at least have the knowledge to pass the exam with at least 50%. Since this is the outro, I'll be honest, I'm surprised if someone's still here. And I'd like to thank any goober who got here. I'm writing this like I'm an actually popular individual, but in all honesty, I'll be surprised when this video gets more than 10 views. Either way, thanks for watching, and I have no outro, so yeah, bye.